So that's how you work out the alternating offers model in that example. Now we'll take a look at the more general case. So more generally, we'll have n rounds be the maximum. And our surplus will be as follows. We have V minus the BATNAs minus all the deltas that have accumulated from the failed negotiations. I can say it's going to come out to 0. Now, I can always let that work, and here's why. Let's say after n minus 1 rounds, the surplus starts out at 1 going into round n. And maybe you're told delta n is 2. That seems to suggest that this rule is incorrect. But as a way you can get around that. So it looks like on the surface, we'd have 1 minus that delta, which is 2, which is negative 1. If the surplus is negative, then there is no benefit at all to working together. Actually, working together is worse than working independently. That means that the players will not negotiate after round n. Now, what if instead we had set delta n to be 1 instead of 2? So if I had just rewritten that. So we start out with 1. Let's subtract off delta n, which is now we're saying to be 1, which is 0. And that means, again, there's no remaining surplus, so no incentive to negotiate. So these end up being equivalent. So you can always set delta n in such a way that the surplus is 0 after n rounds. So you can always make sure that this is true. So don't worry about that assumption. It's actually well-founded. All right, so what's the general solution to this problem if we can safely assume this is true? We can make that safe assumption. So if you rearrange that equation, what you would get is, I'll push all the deltas to the other side over here. So we left with the initial surplus over there. So the original surplus is going to be equal to the sum of all those deltas. So we know that in round N, the player making the deal there is going to say, there's only delta N left. I get that. You get 0. So it's like in our earlier example, when there's just 1 at stake in round 9, then player A said, I get 1, you get 0. If you say no, you get 0 anyway, so you might as well accept. Again, you can throw in a penny if you want to make sure they're not indifferent, but that's the idea. So more generally, instead of dividing 1 and 0, you'll say, I get delta N, you get 0. That's the generalized approach. So then in round N minus 1, we have delta N surplus, but then we also have delta N minus 1 surplus because that has not gone away yet. So if negotiations fail, this last one vanishes, will be over here. But right now, when the offer has not been made yet, then this is the surplus. So we know that in round N, our opponent's going to get delta N for themselves. What we do is say, you get delta N right now, and I get the remaining delta N minus 1. So it's like in our earlier example where there was 2 at stake, and B said, I get 1, you get 1. Because they knew A could get 1 in round 9, so you give A 1 right away, so that they will say yes. This brings us to round N minus 2. So you start with delta N, and then we had delta N minus 1, because this round of negotiations has not yet failed. We also have delta N minus 2. So if you're making the offer here, you know the other side is going to make the offer next round. and they're going to get delta n minus 1. So you offer them at least that to get them to say yes to you today. So what's the remainder to keep? So if they're getting that, then you get these guys. So what happens if you continue that pattern? You go all the way back to round 1. So you figure out who would be making the offer in round N, and they're going to get, right now, delta n plus delta n minus 2, and continue the pattern, delta n minus 4, delta n minus 6, that's their share of the surplus. Similarly, the other player is going to get delta n minus 1, what I showed back here. If you offer around n minus 1, you can secure for yourself delta n minus 1. By the same reason, you also get delta n minus 3, delta n minus 5, so all the odd ones. And that's how you would solve these games. So that wraps up our alternating offers model with diminishing surplus. One last note before I move on to the next section. So in these models, because the surplus goes down, players have a strong incentive to agree immediately. In the real world, though, agreements do not always occur in round 1. Sometimes unions don't just threaten to go on strike, they actually do go on strike. I mentioned earlier the example with the grad students at the University of Oregon. They did go on strike, it did not end instantly. So why does that occur? Does that mean our models are wrong? I'd argue it's not necessarily a disproof of the model. These equilibria are based on if you know the deltas and if you know the other side's BATNA. Now, in the real world, there's often quite a bit of uncertainty about what the other side's BATNA truly is. So if you both misjudge the other's BATNA, then you might make the wrong offer and not come to an agreement right away. If you judge the BATNAs correctly, then you get an agreement in round 1. So I think that's what explains why you don't always see immediate agreements. BATNA is not observed directly. If you try to ask the other player what's their BATNA, they might try to deceive you. So if you're negotiating with a potential employer about a job, you might exaggerate, I could get a ton of money if I take another job instead, so you gotta offer me even more to get me to come here. So you have an incentive to exaggerate. They also have an incentive to exaggerate as well. Then I'd say, well, I talked to another candidate who's asking for a much lower salary, so why should I hire you and pay you this bunch of extra money instead. They also have an incentive to misrepresent their BATNA. So I don't think the model's been disproven at all. It's really just about uncertainty about BATNAs and deltas. So that wraps up this episode. Be sure to join us for our next episode, which will look at another model of bargaining.